You can start. Yeah.
All right. Well, first of all, I'm really happy to be here, and I'm so grateful for the whole Italian and C++ community for having me here, and for the great hospitality I've been shown. And I have to advertise Italian C++ community. This is the website. And today, I'm going to talk about functional techniques in C++. And I've been spending a lot of time with functional programmers lately. So there is a completely different approach to solving problems in functional programming. Like, you always start from the very beginning. Like, what is the meaning of life? So I will start by asking the question, what is programming? What is programming about? And like the low-level answer to this kind of engineering answer would be, we just tell the computer what to do. Like, do this, do this, do this, do this, right? That's programming. But there's more to it. I mean, it's not just like telling the computer what to do. We want to solve problems with the help of the computer. So programming is about solving problems, and computers help us with solving these problems. And the question is, how do we approach problems, right? Because we are humans, we have to first know what to tell the computer what to do. So we have to have some methodology of problem solving. And there's really like one big underlying methodology that we humans use for problem solving. And that's dividing the problem into smaller problems, decomposing a bigger problem into smaller problems. And then we solve these little problems, right? And once they are solved, we have to put the solutions back together. So it's decomposing and then recomposing. So I would venture the answer that programming is about composition. I think like this is the most basic thing about it. Our sponsors. Okay, so that's what I think programming is. And for the longest time, I've been a big fan of object-oriented. Why? Because object-oriented programming is about composition. The way you solve problems using object-oriented programming is you decompose them into objects. So objects are your units of composition. So you write your objects, and then you compose bigger objects from smaller objects. Right? So you have a big object inside of the smaller objects. And why is object-oriented programming so good about composition? Because it allows us to forget about what's inside the object. Right? It's called data hiding. Data hiding, implementation hiding. We just hide this stuff. And when we are composing objects, we don't have to look inside the object. We don't have to look at inside the implementation of an object. Instead, what we do is we look at the interface, the surface area of the object. Not at the volume of the object, which may be huge, but just the surface. Right? And that helps us compose things from these objects because we can think about a bunch of interfaces and how they interact with each other. We don't have to know everything about everything. So we limit our knowledge. We hide our knowledge. Oh, I have this authentication. So what happened to me? Because I suddenly switched from object-oriented programming to functional programming, right? What is this big disenchantment with object-oriented programming? So this happened for a reason. This happened because of the multi-core revolution. Suddenly concurrency became very important. And one thing that can be said about objects is they don't compose with concurrency. Objects don't compose with concurrency. Why is it so? Objects are actually a recipe for really bad things. They are a recipe for a data race. Because what they are hiding is the wrong kind of things. They are hiding things like sharing and mutation. And if you remember what the definition of a data race is, it's multiple thread accessing the same memory at the same time, at least one of them modifying it, right? Okay? So, an object does not tell you on the surface, on the interface, what data it's accessing and what data it's modifying. And if it's sharing anything, if it's sharing implementation, it doesn't tell you about that. So you might have a bunch of objects that you want to combine together, but you don't know what they are sharing behind, right? They might have access to the same implementation. They might have access to the same data item. And one of them might be writing. And suddenly, you have a data race. The other thing that objects are hiding, so if you know how to deal with data races, you just use locking, right? But you also hide locking inside objects, right? You want to abstract from your locking. So you say, this object has a mutex inside, right? And whenever you call a method, it just takes this mutex, and that's it, right? But again, if you are hiding locking, you're exposing yourself to the problem of deadlocks, right? Because you never know what locks are taken by the object that you are composing. You compose them wrongly, and suddenly they try to use each other's lock, right? And you have a deadlock. So, objects don't compose with concurrency. And that's the main problem with object-oriented programming. Now, functional programming has been dealing with concurrency already for a long time. And they have figured out a lot of solutions in this area. And one of the biggest discoveries is immutability. You can have immutable objects, objects that never change, and immutability composes extremely well with concurrency. So if it composes with data hiding, you can hide immutable objects inside other immutable objects and forget about them. It composes with data sharing. You can share immutable objects. Because since nobody is modifying them, right, you will never have a data race. So it's okay to share. Sharing for reading, if you remember the definition of data race, it requires that at least one thread is writing. An immutable object is immutable. Nobody writes to it. And they don't introduce any long distance sharing. They don't introduce coupling between objects. Even if they are sharing the same thing behind, right? It never happens that some object, some faraway object modifies something and suddenly you see the result of this in another object. If the data behind it is immutable, nothing changes. There's no long distance coupling. and they require no synchronization because there is no possibility of data races. But you might be saying, okay, but you cannot program with immutable objects, right? I mean, if nothing in your program changes ever, right, your program is not doing anything.
It's
right?
a constant problem.
Yeah, it's just heating the processor. I mean, you can use your computer for as a source of heat in Siberia, but that's all, right? So it's not that simple. But what functional programming allows you is to control mutation through functional programming. Okay, and the way to do this is how it's done. It's done using so-called persistent objects, persistent data structures. So the idea with a persistent data structure goes back to how do you create an immutable object, right? Every immutable object has to be created at some point. When an object is created, you have to mutate something, right? You are building objects from something. So you have to like adjust some pointers, initialize some values or something, right? So an object is not immediately born immutable. It goes through this phase of being constructed. And during this construction phase, you have mutation. So what if you replace mutation of adult objects just with the mutation of these baby objects when they are being born? And this is something that will still compose with concurrency, because when you are creating an object, it's just one thread creating an object, right? When it's done creating with this object, it can start sharing with other threads, but from that point on, the object is immutable. Now, moreover, because sharing of immutable object is safe, you can create bigger objects from smaller objects. You can reuse objects when you are creating bigger objects. So you can compose smaller objects during construction. And this is something that you will see a lot in the implementation of persistent objects, that you give them, in the constructor, you give them all the parts. And these could be huge parts, right? But since these parts are immutable, the constructor of an immutable object simply just moves a few pointers, points to these parts, and that's it. So the construction of these immutable objects is really quick. It's usually constant time construction. You try to make your objects, you try to make your objects in such a way that it's either constant time construction or at worst logarithmic time construction when you are dealing with trees. And rather than copying, so it looks from the outside as if you were always copying objects, because you always deal with your own copy of the object. But what happens really in the implementation is that you are sharing as much as possible between objects. And because of this way of creating new objects from old objects, from just reusing old stuff, the old versions of objects persist. They are always available. You never destroy the old version of an object unless you explicitly want to get rid of it, right? But you are creating one version of an object after another, and the previous versions of the object persist. That's why they are called persistent objects. This has nothing to do with persisting on disk. Okay, that's a new language in functional programming. persistent objects are just these objects whose versions persist. Okay? And this allows you to, so how do we replace mutation with persistent objects? If you give me a persistent object and say, you know, I just want to modify this tiny piece of this object. How do you do this? Conceptually, you just take this object, create a copy of it, and mutate this little part, right? And you have a new version of the object. The other version persists. But because these objects are immutable, what really happens behind the scenes is you are reusing almost everything from the old object, except for this little part that you are modifying. Okay? Sometimes it's a little bit more complicated. If you have a tree and you want to like remove a node or add a node, at most what you have to recreate is one branch, the path that leads to this node. So mutation of trees is bound by logarithmic bound, right? It's not linear. And of course, because you have no mutation, there's no danger of data races. So this solves the problem of data races. This also solves the problem of deadlocks, because you never have to lock anything. Now, what are the cautions? What are the problems with this that you have to be aware? I'm not saying that this is something that's hard to solve, but this is something you have to keep in mind. Every time you create an object and then you say, from now on this object is immutable, okay? There is this synchronization point, it's called publication point, where you are telling the rest of the world, here, there's an immutable object, okay? This is a synchronization point. It's not enough to just say, now you can use it. There has to be a way of telling the processor as well, now this object is done constructing. Because the operations that are done during construction, all this pointer manipulation and so on, this does not immediately become visible to other processors if you are in a multiprocessor environment, right? They are done in your local cache. So there is a cache coherency thing and so on. So what usually happens is that you are creating an object in one thread, and then when you want to notify other threads about it, you are passing it some way. There is some way of passing objects between threads. Either you create a new thread and pass this object as an argument, or you are using some kind of message queue to pass this object. In any case, this mechanism of passing objects to other threads, this is always synchronized. There's always some kind of synchronization in the implementation of these message passing objects or in the constructor of the thread. So this is a non-existent problem, but it's good to know about this. The bigger problem, and this is mostly a performance problem, is resource management. Okay, in functional languages, this problem is solved mostly by garbage collection. Okay? In C++, we don't have garbage collection. So all this massive sharing that's going on with immutable object, with persistent object, all this has to be handled by hand. Okay? Not really by hand because we have shared pointers. But it has to be handled by shared pointers. Okay? And shared pointers are not the best garbage collection method. They are actually pretty lousy. So if you don't have to use shared pointers, I wouldn't recommend that. But this is one case in which shared pointers play a crucial role. You just can't do this stuff without shared pointers. But what you get in what you get instead is you are creating data structures, these persistent data structures. If you look at it from the implementation point of view, with all these shared pointers, you are creating log-free data structures that are safe. You know how hard it is to create log-free data structures, right? I mean, people have been writing papers about log-free data structures. And sometimes they discover a mistake in a paper and they have to retract it years later. So it's very hard to write log-free data structures. Now, if you are using this approach with persistent data structures using shared pointers are log-free. Shared pointers have synchronization because they have to increment reference counts from multiple threads. So there is definitely synchronization, but they are log-free. Doesn't mean it's cheap. Log-free doesn't mean cheap, right? But you build these log-free data structures, and they are guaranteed to be correct. Well, guaranteed in the sense of, you can never guarantee anything but in programming, but at least they are not much more complex than regular programming. So this is my theoretical part, and now I want to show you how this works in practice. So there is actually a very good book, but it's written in Haskell. So it's about concurrent and parallel and concurrent programming by Simon Martin. So I read this book and I thought, oh, I'm going to implement all this stuff in C++. And I did implement some of these algorithms in C++. And there's one algorithm, very nice algorithm, that's a conference scheduling algorithm. Okay, but it's a little bit too complicated for a talk. So I thought I'll find a simpler algorithm that demonstrates exactly the same problems, and it's the 8 queens problem. How to position 8 queens on a chessboard, right, so that they don't attack each other. And it's a classic problem, and it's been solved by people like Dijkstra. He wrote a paper about it using a backtracking algorithm and demonstrating the principles of programming. And it's not easy. It's not an easy problem to solve using backtracking. I mean, you have to keep a lot of state, and it's difficult to not make mistakes. And when you read this algorithm, it's not really obvious how it works. So it's more about implementation than about the idea of how to solve this problem. Okay? So I want to show you a solution of this problem that is very simple. At least conceptually it's very simple. And then take this conceptually simple solution and convert it into simple code that just reflects the way you think about the problem. Right? So how do you think about this problem? Well, it's one of these divide and conquer problems, right? So suppose that and sort of a recursively solved problem. Suppose that I have positioned k queens already. Okay, I filled the first k rows of my chessboard, right? So what next? And they don't attack each other, right? So it's a partial solution. Well, first let's check. Am I done have I already filled 8 rows? Or n rows in general, right? If I'm done, then just return the solution. Great. If I'm not done, then I have to refine my problem, right? I want to position the next queen in the next row. So I will generate the refinements. I will generate 8, at most 8, possible partial solutions, right? Now, the question is, if I can't if I can't find any solution for the kth row, what do I do, right? And this is where this thinking, this algorithm differs from the other approaches. Normally you would say, okay, I have to backtrack. So I have to undo something, right? I have to go back to my previous solution, and maybe if I've exhausted all the positions in that previous row, well then I have to go back to the previous one, and so on. I have to keep some kind of stack of my moves, and I have to define the undo, and so on. So this stuff gets a little complicated. I mean, it's not horribly complicated, but it's kind of complicated, right? Now, this is not true if I'm using persistent data structures, because I never have to go back, right? All my previous stuff already exists. So here, you're just saying, okay, let me generate these potential solutions, this new row of partial solutions, right? And for each of them, just apply the same algorithm. That's where the recursion comes, right? Just go ahead and apply the same algorithm. And you are always, conceptually, you are dealing with all of them at the same time, right? And also here there is a big difference between this backtracking algorithm and this one. I said you are dealing with all of them at the same time. Automatically, I'm getting concurrency, right? So I'll show you how concurrency comes out of this, right? So here's this algorithm as I described it, right? It's very simple. Partial solution, if k equals dimension 8, let's say, we are done. And generate partial solutions with unchecked queen in k plus first row, right? And then repeat, recursive, right? But this algorithm is extremely general, right? It actually has nothing to do with positioning queens on the board. This is just a generic divide and conquer algorithm, right? So why would I even bother solving the 8 queens problem if I can write a completely generic divide and conquer algorithm and just see which points here have to be specified for my particular problem, right? And this will be the point where I will plug in the moving parts, right? But the template for divide and conquer is always the same. And this is how you think when you're doing functional programming. You are coming up with these generic solutions that are really otherwise hard to think of. So now C++ code, okay? This thing implemented in C++, okay? Let's look at this. So, now I translated it from Haskell. In Haskell, these pluggable things were actually functions. In C++, I just made a class, okay, and made these functions methods of the class. So this is parameterized by 2 things. By this partial solution, there is a class called partial solution, that I will be plugging in depending on what problem I'm solving. But now just think about very generic divide and conquer. I have partial solutions, and I have some kind of constraint that tells me when I'm done. In our case, this constraint is just the number of rows, 8 in particular. It can be any n, right? But in a general algorithm, this constraint could be, you know, have we covered all the possible talks in the conference, right? When this is a conference schedule. So I have this function called generate. This will be my recursive function, and it returns all possible solutions. So a solution to the problem will have some specific type, right? It's not the same as partial solution. Partial solution usually contains more information because it keeps track of where you are. A final solution is usually a simpler thing. So I'm just defining solution type as some member, type def inside partial solution. Okay? So what generate returns is it will return a vector of solutions. Simple. Takes a partial solution and the constraint. The first thing I'm doing is I'm type defing this because I'm going to use it later, so this is just a technical thing, right? And now I'm following this algorithm. Am I finished? So is finished should be a method of partial solution. Partial solution knows when it's finished, I pass it the constraint, it checks, am I finished? Okay. If I'm finished, then I generate this vector of solutions with just one element, the one that I have just found, and return it. Okay? And as you will see, these elements will get accumulated later as I come back from recursion. But at this point, I have just one solution, and I'm returning it inside a vector of one element. Else, if I'm not finished, then I want to refine, okay? And the refinement means partial solution, give me all possible refinements of this. So divide the stuff and give me the refined solution. Give me a list of partial solutions. The new one, corresponding, in the case of queens, it corresponds to new positions of the queen, all possible positions of the queen in the next row. Right? And returns me the whole list. Now I go over this list. I allocate some solution vector that I have just typed def, right? And I do for each, take this partial list of partial solutions, iterate over it. I use a lambda. Thank you for introducing lambdas, Marco. And the lambda takes the partial solution from this list and recursively calls generate with this partial solution. Okay? And generate, what does generate return? It returns a vector of final solutions. So I have to append these final solutions to my vector where I'm accumulating all these final solutions at this point. Right? So this is a vector that just accumulates final solutions because each of these branches could return some. Some of them will not return anything. Some of them will return some final solutions. Right? So whatever final solutions I'm getting, I'm just accumulating them using this copy back inserter. And finally, I return a list. And that's it. And it's a very generic algorithm, right? And the only thing I have to implement now to solve the 8-queen problems is this class partial and constraint. Right? And I'm going to do this. And by the way, exactly the same skeleton, the same function, the same template function is used to solve this problem of conference scheduling. No difference there. So here's the class partial solution. And this is where the persistent stuff comes in. Okay? This is a persistent class. You'll see why. So as I said, I have to type this final solution type, right? Final solution is just a list of positions. So in fact, I have something called position, which is like the XY coordinate for the queen, right? And the partial solution is just a list of these positions, right? And current row. That's my partial solution. When I'm done, right, I have this list filled with 8 positions, and that's my final solution. Okay? So final solution is just a list of positions. Now I have 2 constructors. One is to construct the null solution, the one that I will begin with. Right? I have to begin somewhere. So that's an empty solution. Current row is equal to 0, list is empty. The other is this constructor that I mentioned, how you construct persistent objects. Right? It takes a huge object, in this case, it's a list of positions, right? And combines it with some other data very quickly, and it shares whatever was passed to it, right? So notice, it takes a constant reference to a list of positions, and the list of positions is this immutable list. It never changes, okay? That's one of our persistent objects, it's a persistent list. I'll show you the implementation in a moment, right? So it just remembers current row and the list of positions, and that's it. So that's a very quick construction, right? Get solution obviously returns the list. Is finished takes this constrained object, which in our case is just type def to an integer, and checks is current row equal to the dimension. That's it, right? And then there's the refine method, and all this logic is in the refine method. But it's also a very simple logic in the refine method. Now look what the refine returns. It returns a list of partial solutions. Okay? So that's very important. And notice also, all these methods are constant. None of these methods modifies the object. So here's the refine method. It takes dimension, so it takes the constraint that we need, right? And it just goes over the row from the beginning to the end, so these 8 possible positions. And for each of them, calls the method is allowed. So that's a very 8-queen problem-specific method. Is this position allowed? It just checks, am I under check from any other queen? Right? And if this position is not allowed, then we just skip it. Right? If it's allowed, then, and this is a very important thing, what's happening here, okay? So I'm creating a new partial solution. How do I create a new partial solution? I'm using this constructor for partial solution, right? What do I pass this partial solution? I'm passing it a new list of queens, right? Which is the old list plus the new one, the one that I'm adding, right? So I'm calling this method push from, and that might look like a mutating method, but it's not, because this is my persistent data structure. It never mutates the original. What it does, it returns me a new list that contains the old list plus the new queen, plus the new position, right? Now, it does not copy the old list because it doesn't have to, right? Because the old list is immutable. It can just point to it, right? So it's a cheap operation. So it's like push front is a cheap operation always, right? It's constant time. This one is constant time too. So the complexity of this solution is trivial. So that's it. And I'm looping through it, creating this list of new solutions, and just returning it. And I wrote this the push front method here. It returns a list. Now it looks like it returns a list by value. And it does return a list by value, but the list internally has a move constructor, so it's really moving, right? And it's const. It does not modify its source. And this is very important because I'm reusing the same tail for all these lists in a row, right? This is my partial solution up to here. And it becomes the tail of my list when I'm adding the new, I'm adding the new position at the head of the list, right? I'm pushing it, right? So I'm reusing the same tail with all of them. So now you can see how persistence and backtracking really do the same thing, except that persistence makes it so trivial, so easy, right? I don't have to go back and undo stuff, right? Because I don't destroy anything. All the stuff that I've been using, in this case, it's this tail, right? And the tail of this tail and the tail of this tail, when I go many, many levels of recursion, it's all persistent. It never disappears. So when I pop in, you know, I just go back to the previous one. You know, at this point when I'm creating a new partial solution, I'm going then with this partial solution I'm going to generate in the code above, right? It does not destroy this. It does not destroy any of the tails that I'm still waiting for evaluation, right?
But this looks a lot like when you build type lists in metaprogramming, right? I mean, the concept of having a tail and adding something at the beginning. You're just composing immutable concepts into a higher level.
So you're talking about template metaprogramming?
Right, yeah.
Okay, template metaprogramming is by definition functional, right? Nothing is mutable. So, I mean, if you are a template metaprogrammer, you know all this stuff. Because that's how you program. That's how you program in templates. But this is something that you do at runtime here, right? So, it's applying the same methods, but... So, as I said, using persistent objects, the main reason for using it is that you can make them concurrent, right? We started with solving the concurrency problem. So how do you make this algorithm parallel? How do you parallelize this algorithm? And normally if somebody told you, you know, okay, here's a C++ program that does the 8-queen solution and does backtracking and so on. Now, go and parallelize it, right? This would be hellish experience, right? I mean, so what do? I would have to like rewrite the whole algorithm. I would have to change the algorithm to begin with, right? I cannot use the same algorithm for parallel. Now I have to worry about sharing data. I have to worry about locking while I'm mutating, right? As if I'm, you know, I have multiple threads, I'm changing state, I have to do some locking. Do I get into a deadlock? Right? What is the cost of all this locking? Whereas in this case, making this algorithm parallel It's almost trivial. It's just shouting, make me parallel, right? I mean, so you have this list of partial solutions and you are looping over it. Why not make this looping in parallel? Do I have to introduce any locks or anything? No, because I'm never modifying anything, right? So this algorithm parallelizes trivially. So I'll show you how to parallelize this algorithm, but first let's think about one more thing. If I want to make this algorithm parallel, I mean, making it parallel means I want better performance out of it, right? So there's usually this problem of the granularity to which I want to go with making it parallel. Like if I go all the way and make you know, every move in parallel, like setting one queen position in parallel with all the others, I will probably create like 1 million threads because it's a huge tree, right? So usually what you do is you want to throttle down parallelism to a certain level. So like you say, okay, to the depth of, let's say 3, let's do everything in parallel, and from the depth of 3 down, let's do the serial algorithm, right? It's like when you are sorting stuff, you also do this parallel sort to a certain level, and then when you only have to sort like 100 items, you just do a quick sort or bubble sort or whatever, right? So you switch these algorithms. So let's do this. So let's take this algorithm and make it parallel and also add the depth. So we'll check for the depth, and if the depth is greater than a certain level, we'll just go back to our previous algorithm. And it turns out that all the parallelism that's necessary here is actually in the skeleton, in this divide and conquer skeleton. We'll parallelize this skeleton. We don't have to think about the particular 8-queen problem. We'll just parallelize this generate function that is very generic. So here it is. Now I'll walk you through this. So this is generate par. It takes one more argument, this depth that I mentioned, right? Otherwise it's the same. The first thing it checks is the depth 0. Okay, so it decreases depth with each level of recursion, right? Until it reaches 0. So if depth is 0, then call my previous function generate, the one that I showed you before, right? Which is a serial function. Excellent. Otherwise, well, check if it's finished. If it's finished, then return partial solution, no change, right? The change comes here when we are generating this refined solution. So we call it refine, we get a list of solutions, and now we want to go over these solutions in parallel. So the preparation for this is, since I'm doing it in C++11, right? I will create these asynchronous tasks, and these asynchronous tasks, instead of returning the result, they return the future of the result, the promise of doing this in the future. So it's a future of the result. So I have to have a vector of futures, okay? So it's a vector of futures, and they will store solution vectors, because that's what refinement will give you. The generate thing will return solution vectors, right? So I have this vector of futures, and then I do for each, and a lambda, and it's almost exactly the same, except that I'm calling generate par inside the lambda, that I'm passing to standard async. Standard async creates a new thread and runs this lambda inside the thread, and it returns a future. So it returns this future, and It's a future of vectors, right, of solutions. I do pushback of this future to my big vector of futures. And then after this, I just wait for all these futures to finish. Okay? So this is a method when all vector takes a vector of futures and waits until all these futures are done doing get on each of these futures. This is actually something that in C++17 will be part of the library. Right now it's not. And then I concatenate all of these things just as previously. So making this skeleton of divide and conquer parallel was virtually trivial, right? So, I don't know, how much time do I have?
Maybe less than 5 minutes, I think.
Okay, then let me quickly show you the implementation of the persistent list, because this is the implementation of the simplest persistent data structure. There are many other persistent data structures that I have implemented some of them. I put them on GitHub, but this is like the basic one and shows all the principles of how do you implement persistent data structures or functional data structures. So this is how you define data structures in a functional language. You say, what is a list, right? What is the meaning of list? A list is either empty or it consists of a head and another list that we call tail. Okay? And because this is a persistent data structure, it never changes. After I've constructed it, that's it, right? So I really have two kinds of lists, empty lists and non-empty lists. So how would I implement this? Would I put a boolean there saying I was created empty or not? Well, in C++, we'll just use a pointer, right? A null pointer will mean I'm an empty list. The non-null pointer will mean I'm not empty. So here's this the implementation. So here look at the constructors first, right? So two constructors, because the list can be either empty, that means one constructor, null pointer for head, or it can be an element, head, and a list tail. So this description of what a list is translates directly into two constructors. Right? The implementation is that I have a pointer to an item, that's my head. So if it's null, it means I'm empty. If it's pointing to an item is just, a singly linked list, the usual implementation. Now this doesn't take into account memory management. This is, if we had garbage collection, that would be it. That would be great, right? And these are the methods. Is empty, obviously, front. Now these are interesting, pop front and push front. These are the methods that are const, right? Because I'm creating a persistent list, persistent data structure, I will never modify anything. So pop front just returns a new list, which is just the tail of my list, right? And it will never be modified because lists are never modified. So I can return a list which contains a pointer, two elements, and they will be shared, right? This list is just a pointer, nothing else. So I'm returning this pointer. Push from, it calls this constructor of a list, right? That takes a value and this list as its tail, also sharing, right? So there's no copy. And because we have no garbage collection, we have to use a shared pointer. And shared pointer will make this automatically thread safe, which is good. Bad thing is it's expensive. So here are the changes I have to make to this list. And they are also extremely simple, right? Instead of pointer, I have shared pointer. Now, when I'm creating a list from the tail, I have to allocate a new shared pointer for my new list, right? And this is the make shared that Marco talked about. Make shared will make sure that we have locality of reference. This is very important, the locality of reference, that there will be no two allocations. It will be one block of memory which will contain the reference count and the object, the list, right? The item. The places where reference counting takes place, there are two places. One is the destruction, which you don't see a destructor here, but the destructor of shared pointer dereferences, changes reference count, and deallocates the tail. Let's say. The other place is in the construction of item when you are attaching the tail, right? This is where you are incrementing the reference count of the tail. So this assignment here, next equals tail, that's where the reference count is increasing. So I'm almost done. So the ease of use of this is extremely important. The implementation follows the algorithm. The way I described it to you, this is how it was implemented, right? It's composable. I was composing bigger immutable objects from smaller immutable objects. It's orthogonal in the sense that I could have separated the implementation of the 8-queen algorithm from the divide and conquer algorithm. I was able to separate parallel implementation from sequential implementation. There's also one other implementation that I was not talking about, it's the lazy implementation. It's also possible. Performance is not very good, I must say. And there are several reasons why. And mostly it's because of memory allocation and deallocation. The memory management in C++ is just not built for this kind of stuff. So whatever you've heard about C++ having great memory management, it's because it's optimized for one type of use. It's totally not optimized for this kind of usage. And I think that's a big shortcut. All this stuff is available on GitHub. And I have queue, stream, red black tree, leftist heap implemented as persistent data structures. Okay. That's it.